Okay, can you see my screen now?
Yes, we can see your screen.
Okay, let me just move to the presentation mode. I hope this is clear. Is it okay?
Yes, is it okay?
Okay, good. Okay, so I'll start. So thank you very much, first of all, for inviting me for this very nice conference. Of course, I prefer to be in Indonesia now, but unfortunately, because of this virus situation, basically, I'm presenting this basically keynote lecture from Glasgow, Scotland. So I hope you guys will find time to visit us here in Glasgow in the near future. So today, I would like to present peridynamics and past, present, and future. Basically, I will just try to give you some background information about peridynamics, what that is all about, and so on. So before I start, let me just give you a brief outline of my talk. I presume that many of you may not be very familiar with the term peridynamics, so I will try to briefly explain what that is all about. And I will talk about its history, what we are currently working on, and also I will also emphasize some potential future areas. So what is peridynamics? So peridynamics is a new continuum mechanics formulation. Why do we call it's new? Because peridynamics uses integral equations as opposed to partial differential equations that we normally use in classical continuum mechanics. And these equations, as you will see, since we are using integral equations, they bring certain advantages. So that means that we can analyze problems which includes discontinuities. When I say discontinuities, I normally talk about cracks. So basically, this is a technique which allows us to predict how cracks initiate and how they will evolve. And another nice part or nice feature of this technique is with respect to some other methodologies, because peridynamics is not the only technique which does similar calculations. Basically, this particular technique requires or does not require crack growth law. So that means that we don't need to tell our code when the cracks will basically initiate, in which direction they are going to propagate, and when they are going to branch, and so on. So although we are using a failure criterion, but it's much simpler with respect to many other techniques. And also cracks, although we normally use peridynamics to simulate cracks, cracks are not special objects in our formulation. They are just part of the formulation. So that means that we can have as many cracks as possible in the system. So we can have hundreds or thousands of cracks without any problem. So which is very difficult to do if you want to use some other methodologies. So I hope my voice is okay so far. Okay. Okay, so basically, before I move on, let me just start from basics in case some of you are not familiar with continuum mechanics, because as I said, peridynamics is a continuum mechanics formulation, and for me just to show its difference with respect to other formulations, let me just briefly describe what continuum mechanics is all about. So continuum mechanics is a formulation that we are using to find out what happens to structures if they are subjected to external loading condition, as you can see in here. So basically, you can think about any structure that basically which are subjected to this loading condition. And in structural mechanics, we are very much interested in what happens to our Okay, I think we are back. Okay, so let me just continue. So as I said, in structure mechanics, we are very much interested in the deformation of structures if they are subjected to external loading condition. And to do this, as I said, we are using this continuum mechanics methodology. And to actually obtain our solution, we assume that the structure that we are analyzing is composed of small volumes that we call a material point, as you can see in here. And continuum mechanics is basically describing how these volumes are also deforming as a result of loading condition. And there are many different types of formulations that we use for continuum mechanics, and probably the most common one is called classical continuum mechanics. And classical continuum mechanics was introduced by Cauchy. And according to his formulation, basically he made a certain assumption in a way that a material point inside the system can only interact with the material points in its nearest neighborhood. So as you can see, this blue material point is only interacting with the ones which are shown in green color. And he defines the interaction between these material points by defining a vector that we call T, or traction vector. So this traction vector allows us to define the information transfer between neighboring material points. And what he did basically is he used some physics laws that we normally use. So he started with the global balance of linear momentum, and then to obtain basically his equation of motion for each material point. And then he introduced a parameter that we currently use very much in structure mechanics that we call stress. So he related the traction vector to the stress tensor. And once he basically substitute this quantity in the balance of linear momentum, he was able to obtain equation of motion of a material point. So here, rho is the density of the material, u double dot is the acceleration of the material point, sigma is again our stress tensor, and b is the body force. So this is a very useful equation, and people are using this equation for a long amount of time. So almost like 200 years to analyze many different problems. So it's really a great equation to use. But unfortunately, it has also a deficiency. And the deficiency is coming from this particular term. As you see, we have this differentiation of the stress tensor. So since, if you think about, for example, cracks inside the structure, because of the cracks, our displacements are becoming discontinuities along the crack surfaces. So is everything all right, Yuli? I cannot hear you. Okay, because I'm not 100% sure.
Yes, it's clear.
Okay, good. Okay, so basically, as I said, this is a very good equation, but because of the differentiation or derivative in this particular term, and for the case of a crack, the displacements are not continuous along the crack surfaces. That means that we cannot define strain and also stress at those locations. That means that we cannot use these equations if you are dealing with cracks. Okay, so then that means that we need to find an alternative solution. And Dr. Stilling, since he was aware of this particular situation, he came up with a new continuum mechanics formulation that he called Peridynamics. And this formulation is somewhat different with respect to what Cauchy basically introduced earlier. So according to Dr. Stilling's new peridynamic formulation, he said that all material points inside the system actually can interact with each other. So it is very similar to how atoms are interacting with each other. And Also, as you can see here, we have these two metallic points, and you see this. These are the dynamics that two metallic points are exerting on each other. So basically, as opposed to traction vector that we just saw in the Cauchy's formulation, now we have peridynamic forces which are describing the information transfer between metal points. And these points, they can be far from each other. They don't need to be in their nearest neighborhood. And then what he did is, instead of using Cauchy's formulation, he introduced a new equation of motion to describe the motion of a metal point. So if you look at these two equations, this is the Cauchy's one, and this is the peridynamic equation. They look almost the same, except this term here, the problematic term, which was causing the problem, because this has a derivative. So instead of having a derivative, now we have an integral term here, so that we don't need to worry about derivatives. Okay, so that means that regardless of these continuities in our system, this equation is always valid. Okay, so that is the main advantage of peridynamics. So we can use peridynamic equation if we have cracks in the system or not, if we have any discontinuity in the system or not. So that's the main advantage of peridynamics. So depending on how these forces are basically acting on each other between two metal points, we describe or we classify peridynamics. Okay, so if these forces, basically, as you can see here, they are in any direction, we call this as non-ordinary state-based peridynamic theory. This is one of the most general peridynamic theory that we have. And if we make an assumption that these interaction forces are along this interaction direction, but their magnitude are basically different, then we call this as ordinary state-based peridynamic theory. And if we make a further assumption that these forces, they are opposite to each other, and also they have the same magnitude, and we call this as band-based peridynamic theory. And this is actually the original peridynamic theory that Dr. Silling introduced in 2000. And it's very simple to implement, but it has also some limitations. So if you don't need to, actually, if you don't want those limitations, then you need to use these advanced state-based peridynamic formulations. So how do we obtain actually our peridynamic equation of motion? So where does it come from? Actually, we can obtain this equation based on an Euler Lagrange equation that we know from physics. Okay, so basically, if you use a Lagrange equation, you can obtain basically the equation of motion. Here, L is the difference between the total kinetic energy of the system and the total potential of the system. So how do we calculate total kinetic energy of the system? Basically, as I said, we have metal points inside the system. So if you can calculate this integration or summation of all metal points inside the system, then it will give us basically the total kinetic energy of the system. How about the total potential energy of the system? Basically, it is the integration of the strain energy density of all metal points, and also the energy coming from external forces. Okay, so to simplify our calculation, what we do is, we just do a little mathematical trick. So according to the text, write down now these integral terms as a summation, infinite summation, so that I can do calculations in an easier manner. So what we do is basically we write these kinetic energy and potential energy terms in terms of basically these summations. Okay, so these are exactly the same thing, but as you see, we are now using these infinite summation terms. So one thing that we need to pay attention here is the strain energy of a particular metal point. So in peridynamics, we are defining this in terms of something that we call micropotentials. So micropotentials are basically defining the strength of interactions between two interacting metal points. In this case, we have two metal points, I and J, they are interacting with each other, and this omega ij and omega ji, basically they are defining the strength of the interactions between two metal points. And then what we do is we substitute every Euler Lagrange equation And once we do that, basically we can obtain our equation of motion in this particular form. Here, as you see, we have this inertia term, and here we have this applied force term or load term. Now we have these two terms with the derivatives. So if you again remember from our physics courses, so if you have a potential and if you take a derivative of that potential with respect to either position or displacement, basically that is corresponding to a force. So basically these guys here, they are actually representing an interaction force between two interacting metal points. As you see here, we have J and we have K, and these guys are interacting with each other. And now these forces are basically describing how these forces are basically, or these 2 points are interacting with each other. And if you remember, in bond-based peridynamics, we assume that these two guys, they are equal to each other, but they are in opposite direction. That means that, this 1/2 term can disappear, and we can obtain now our final equation of motion of peridynamic theory. So, if you look at the simplest bond-based peridynamic formulation, we have an important parameter that we call horizon. So what is horizon? So basically, as I mentioned earlier, a metal point can interact with all metal points inside the system. But as you will see, we normally do our calculations by using computational methods. So if you take into account all interactions, basically, it's impossible to obtain a solution. So what we do is we just define an interaction domain or influence domain, so that outside of this domain, we assume that there is no interaction, and this domain is called a horizon. So how do we calculate this interaction force between two metal points? So in simple sense, you can think about this force as a spring force. So you can think about 2 points, and there is a spring in between them. Okay, and as the spring is deforming, you create actually a force in the spring. But we just write this force in a little bit different form. So instead of saying spring constant times the change in length of the spring, we just introduce a parameter that we call bond constant and a stretch. So what is stretch? So basically stretch is the change in length between two metal points, so change in distance between two metal points after the deformation, divided by the original distance between two metal points. How about bond constant? Bond constant is actually our material constant in this new formulation.
Remain 10 minutes.
10 minutes, okay. So basically bond constant is our material constant of this new formulation. And basically the good news is we can calculate or we can represent our bond constant in terms of the elastic modulus of the material. That's something that we know for many different material systems. But the problem of bond-based peridynamic theory is, as I said, there is a limitation on our material constants. So if you don't want this limitation, then you need to use this advanced peridynamic formulation. So far, I didn't talk about failure in peridynamics. So it's really straightforward to define failure in peridynamics. So then what we do is we always check the stretch of two metal points. And then once this stretch exceeds a critical distance that we call critical stretch, then we just break an interaction. So that means that our force is basically dropping to 0. And we normally use meshes approach to basically to solve our problems. So that means that we are just dividing our computation domain into smaller volumes, and each volume is represented by a point. And so far I just want to basically describe what peridynamics is all about. Now I want to also show you some simple examples. So as you see, there is a simple example here that we have some type of a glass type of material, which is PMMA. And here in this particular situation, basically we have this diagonally shaped specimen, and there's an initial crack there, and then we apply tensile load from top and bottom. And depending on the crack orientation, as you can see here in a different way. So, and these guys, the gray color ones are basically experimental data, and the other results are from peridynamic simulations. So if you look at basically carefully, you will see that peridynamic simulations actually captured the correct fracture pattern regardless of the orientation of this initial crack. And also, as I said, peridynamics really doesn't care about how many cracks that we have in the system. So this is an example like this. So we have a big crack here, macro crack, and there are small cracks, micro cracks around this. And we want to see how these basically cracks are influencing the propagation of this macro crack. And again, as I said, peridynamics is a very suitable tool for this. So these are basically, these plots are just showing us some peridynamic results, which basically shows how the crack is propagating and how these small cracks are influencing the propagation of this the macro crack. Okay, so as you see, if you use peridynamics, you can have as many cracks as possible, and you can investigate how the cracks are interacting with each other. And in the old days, basically the first peridynamic code was appeared with the name of emu, and emu is actually coming from a bird. I think this bird is mainly found in Australia, and this code was developed at San Diego National Laboratories. And then again, peridynamics is currently available in a molecular dynamics code that we call LUMPS. This is freely available. So basically, if you use this molecular dynamics code, you can also have the capability to use peridynamics. And also, if you are familiar with finite element methodology, actually we can cheat finite element software, and then we can perform peridynamic simulations. So if you don't want to basically write your own peridynamic code, you can use commercial software to perform peridynamic simulations. So as you can see here, we can just generate nodes, and we can create actually springs or link elements in between, so that we have a network of these basically interactions. And once these interactions are broken based on our failure criteria, then we start creating cracks in the system. So just a kind of a history of peridynamics. So what is peridynamics from in terms of name? So peri is actually horizon. So as I mentioned, this is an important parameter in peridynamics, and dynamics is the force base. This name is coming from Greek language. And the first paper appeared in 2000 by Dr. Selling. And as you see, in the initial days, people didn't recognize the capability of peridynamics. But as you see, as the time progresses, now from different parts of the world, many people are working on peridynamics. So it is an emerging area in computational mechanics. And the first actually PhD thesis was written at MIT and Caltech in 2003 and 2005. And in the earlier days of peridynamics, it was mainly used in the design process of the new Boeing airplane, because this airplane was made of composite material, and actually peridynamic simulations were used in the design process of this new Boeing plane. And there is this paper which was written by Selling and Ascari, and this is a very nice paper, very informative paper. So if you want to start learning about peridynamics, this is a very good start. And as I said, the original formulation has a limitation. So if you don't want that limitation, you should use state concept. And this is the first paper actually, which is describing this. And, in the initial days of basic peridynamics, it encounters lots of oppositions, because whenever you introduce something new, people, they don't want to believe that this actual technique can work. And basically it went through all the stages that Schopenhauer described. So all truth passes through 3 stages. First, it is ridiculed. Secondly, it is violently opposed. And thirdly, it is accepted as being self-evident. So basically, peridynamics went through all these 3 stages of truth. And, if you look at the basics of peridynamics, actually, it went back to Navier. So basically, Navier's formulation is very similar to peridynamic formulation. So if you are wondering, basically, if you are interested, so please look at his formulation. Later on, again, there are some other similar formulation available in the literature, but they didn't really look at the failure aspect. But you can find similar formulations by Kroner and also Rogula. And currently, there are various peridynamic books available in the literature. One of them was written, co-authored by myself, this peridynamic theory and its applications. And now this book is also available both in Chinese and also Persian languages. And we actually recently established a journal, which is called Journal of Peridynamics and Non-Local Modeling. And we also have a website, which is www.peridynamics.org. So if you want to basically get more information, please visit this website. And we also established a research center here at University of Strathclyde. And we are basically looking at many different problems, which includes cracks in many different areas. And basically, we have a certain number of students and researchers basically looking at, as I said, different problems. And I just want to briefly talk about what we kind of do presently. So, so far, I mainly talked about structural mechanics, but now many problems includes coupling of different fields. So that means that we need to find out the effect of different fields on each other. For example, the effect of temperature on deformations and the effect of deformations on temperature and so on. So depending on basically the industry that you are interested, basically you may encounter many different type of basic problems like this. So for example, hydraulic fracturing, lightning strike, failure in electronic packages, and then nuclear materials and so on. So in these different areas, you need to couple different fields. And now peridynamic formulations are also available for different physical fields. For example, we now have peridynamic formulation of, for example, diffusion, thermal diffusion. So instead of having this traditional basic diffusion equation, now we have the diffusion equation in integral form, so that we can have basically a single framework, peridynamic framework, which allows us to do multi-physics simulation, and also we can predict failure on top of that. And this is just an example basically that we did for Samsung Electronics. So we investigated, I think I'm approaching my time, that's what I see, but I will finish soon. I will finish soon. So basically, in this particular case, we are coupling three different fields, which is the structural, thermal, and basically moisture together. And basically, we came up with all the formulations and so on. And in electronic packages, basically, we tried to predict how the moisture is affecting and how the moisture is actually causing cracking in electronic packages. And some future areas for basic peridynamics, by using peridynamics, you can do multi-scale modeling. Is a very suitable tool. And you can look at, for example, 3D printed materials. You can do material design by using peridynamics. And also now, this artificial intelligence, machine learning is becoming really popular. So again, you can incorporate these concepts within peridynamic theory. So as a final remark, basically, I just want to say that, peridynamics is a really suitable alternative tool for computation modeling of future problems. And it is also not limited to structural mechanics, but actually you can use it. With that one, I would like to thank you for your attention.
Okay, thank you so much for your excellent and interesting presentation for Professor Erkan. So I would like to continue for the second keynote speaker. And for sorting the time, I would like to introduce the second speaker in the second session. He is Dr. Sulalit Bandyopadhyay. So Dr. Sulalit Bandyopadhyay is a postdoctoral research fellow at Department of Chemical Engineering, Norwegian University of Science and Technology, and TNU Norway. He is also a visiting researcher at Department of Water Management, Delft, Netherlands. His educational background are PhD in Chemical Engineering at Department of Chemical Engineering, NTNU Norway, and his Master of Science, MSc in Chemical Engineering at NTNU Norway, and it is Zurich, and his Bachelor of Chemical Engineering from Jadavpur University, India. He has working experience as research assistant and summer intern at Department of Chemical Engineering and TNU Norway, and he has a lecture and teaching assistant at Department of Chemical Engineering and TNU Norway, postdoc research fellow at TU Delft and EHE Delft Institute for Water Education, Netherlands, and he's also polymer scientist, anti-fouling Jotun performance coating, R&D chemist, second technology development Jotun AS Sandefjord, Norway. He is also very active working in his project with research interests including nanomaterial, polymer reaction engineering, bioprocess engineering, thermodynamic of material, and hydrometallurgy. So for shortening the time, for the Dr. Sulalit, I give opportunities to you to share your presentation in this session. Please welcoming to Dr. Sulalit.
Thank you very much.
You're welcome.
I would also like to thank the organizers for giving this nice opportunity to address around over 230 people in this live setting. I hope you can see my screen and you can hear me.
Yes, I can see
Okay.
your screen and your voice is clearly.
Perfect. Thank you very much. So as also the previous keynote speaker, it would have been a pleasure to be in Surabaya at this time of the year. It was a planned visit as well, but due to the coronavirus situation, it's not possible. And it's also lovely to see so many different topics being covered by this conference. And now I'm going to take you from the world of peridynamics to nanomaterials for biomedicine or biomedical applications. So as the moderator mentioned, that I am working at the Norwegian University of Science and Technology, currently in the capacity of the associate professor and as a researcher at the department, and working mostly towards developing nanomaterials. So what I thought today I'm going to talk about is take you into the world of tailoring these nanomaterials so as to functionalize them for different applications in biomedicine. So just before I start onto the topic, I wanted to give you a brief overview of what I work with, and that is primarily designing and understanding smart nanoparticles. The reason we call them smart is that a single nanoparticle can do several functions. For example, the one that you now see on your screen has a magnetic core, which means that it can be easily separated by magnetic field. And then you have a polymer chain onto the nanoparticles, which respond to stimuli such as temperature or pH. So they collapse as a function of temperature. And then the green dot is representative of a cargo molecule, which could be biocides that are used in anti-fouling paints, or they could be drug which could be in the field of biomedicine. So that is where my research focus and my research group's focus lies. And we are mostly working on synthesis of these various materials, characterizing them, functionalizing them. And currently my research interests are broadly classified into the following 6 hexagonal areas, with a huge focus on growth kinetics and mechanism, a part of which I'm going to talk through you today. And then quite a lot of work on bioimaging, biosensing, and most recently into diagnostics, connection to the coronavirus situation, which I'm going to touch upon briefly as well. We work with photocatalysis with these nanomaterials. A lot of work goes into drug delivery, hypothermia, magnetic resonance imaging for developing contrast agents. And few work also goes on with oil and gas, with collaboration between Norway and in Malaysia. And then much of my work on water management is in collaboration with TU Delft in the Netherlands, where I'm also employed as a researcher, and the Institute for Water Education in the Netherlands, which is an UNESCO-supported institute. And as I said, that this is currently my group's composition with several master students and PhDs. And a part of the work that I'm going to present today is primarily work done by some of these excellent candidates currently working in my group. So the way I've structured today's talk is that first and foremost, I'm going to give you a brief overview, because from the conference program, I saw that there is a variety of audience joining this, and therefore it might be important to kind of go through the very fundamentals. Once I've set the stage for everyone to follow, I would take you to the world of gold nanoparticles and talk about how we tailor their growth at the nanoscale, how we control their growth. Then I'll take you to iron oxide nanoparticles, where I'm going to once again talk about how we are controlling the synthesis and the parameters to affect their shape, size, and morphology. I'm going to touch upon two important methods which we regularly employ in our labs: co-precipitation and thermal decomposition. And then I'm going to take you to a bit of functionalization to give you a flavor of how you can use these nanoparticles, or what we do on the surface chemistry to functionalize them for specific applications. And then I would take you to the last phase of my talk, which is going to be on the corona diagnostic kit development, which is a project that started in late March and is the one that occupies me for the most of the time now in the research life. So as I said, that this lecture is going to be about tailoring. So before you do the tailoring, you need to know what materials you have and what fundamentals you need to understand the growth and kinetics. So I'll first start there. And this is quite common for people with a background in nanoparticles, but not so common for people from other backgrounds in the audience. So I'll go through it very briefly. In order to synthesize nanoparticles, the very driving force is the supersaturation. And supersaturation basically means it is defined in terms of the activity of a certain molecular species in the solution divided by the activity of the same species in equilibrium conditions. So this means that in order to form nanoparticles or synthesize nanoparticles, there should be a driving force in terms of supersaturation. Once you have established that driving force, the first events would happen. The first nuclei would form a step called nucleation. And then the nuclei would start to grow by a fundamental process of crystal growth. Whether you go through a classical or a non-classical approach is not the point of interest right now, but there would be the particles will enlarge or grow in size. And then additional growth continues, which is we refer to as secondary growth or size enlargement through different processes such as Oswald ripening, so on and so forth. So if you want to schematically visualize what's happening is that you generate precursor materials, which could be especially for reactions that require a preceding step to generate supersaturation, most likely a reduction process. And then if you have a fast nucleation, it would result in small nanoparticles, whereas if you have a slow nucleation, you will get bigger nanoparticles. Having said that, I would like to caution you that this is not the only criteria that controls the nanoparticle size, but one of the most important criteria. We'll look into it a bit more details in the next slide through a classical mechanism called the Lammer's diagram. So what it basically talks about is that S here represents a supersaturation. So there is a critical supersaturation required for nucleation to happen. So as you go on, if you follow this curve follow my cursor on the screen, as the concentration goes higher up, S is a solubility limit, the system starts to become supersaturated. But from S until SC, there is no nucleation happening because although the system is supersaturated, it requires an additional kick to form the first nuclei, which can be derived from a classical nucleation growth theory. So once the critical supersaturation for nucleation is reached, the first nuclei form. And as you can see, the nucleation window marked by the region 2 is very narrow. The narrower you can keep it, the smaller the particle size and the more monodispersed particles will you get at the end. Once the nucleation has happened, nucleation drains the supersaturation. So you go down in supersaturation, and below the SC, there is no further nucleation possible, and growth continues for the later part of the process. So what this diagram basically or conceptually does is that it separates nucleation and growth on an energy landscape and makes it easy for us to understand how nanoparticles form. So from there, I would like to take you to the two kinds of nanoparticles that I mentioned I'm going to cover a bit The first and foremost is gold nanoparticles, and why the cry over gold nanoparticles, why so much interest in using gold nanoparticles for a variety of applications. So the most important property that is used for gold nanoparticles, it's called LSPR, or localized surface plasmon resonance, schematically depicted by this diagram here. So what happens is that when electromagnetic frequency, which can be light wave, is incident on gold nanoparticles, the electromagnetic wave gets trapped inside the nanoparticles, causing resonance, and therefore you see this dipolar resonance happening, and this results in two important things. So this property is a size-dependent, shape-dependent, solvent-dependent property, meaning if you're able to tune the size, shape, solvent, and other factors, you would be able to tune the performance of these nanoparticles. More importantly, for gold nanoparticles, this happens within the UV visible range, meaning the beautiful color of gold nanoparticles from pink to purple is because of this property LSPR, and that makes them exciting candidates for optical imaging, etc. So what it literally translates to, for those of you wondering, this is a fundamental property, how do we make use of it, is that if you are detecting gold nanoparticles using UV-vis spectroscopy, you'll be able to see that there is a huge difference the moment you change the size and the shape. So for a typical gold nanoparticle, it is located around 520 nanometer, this LSPR peak. The moment you have anisotropic rods, which means you have two axes, a long longitudinal axis and a short transverse axis, you get two peaks, one around 520 nanometer, the other one in the longer wavelength. And then if you further increase the aspect ratio, then you shift this to longer wavelength. And this is interesting for different kinds of applications. If you have a small aspect ratio, nanorod as we call them, then they're very good for photothermal therapy, which means that you shine in light, it absorbs the light and produces heat, and that heat can be used to kill cells. On the other hand, if there are large structures, the larger nanorods, they are super useful because of their scattering properties in optical imaging. So you can use them as contrast agents to view inside the cell much better than you could do without a contrast agent. And the other kind of nanoparticles which I'm going to talk to you today about are the iron oxide nanoparticles. And the major reason why they have been of such interest is their superparamagnetic properties. What it means that if you're familiar with this MH curve, which is the hysteresis curve for magnetic materials, a superparamagnetic material is the dotted line shown here, meaning the hysteresis area is very low, almost negligible. It has got high magnetic saturation. It behaves as a magnetic material only in the presence of a magnetic field. The moment you take it out, it loses its magnetic properties. As a result of this, iron oxide nanoparticles have found wide applications in a host of biomedicine subjects, including magnetic resonance imaging. So then quickly to a host of applications. I'm not going to take you through all of them, but tell you that these nanoparticles, if you're able to functionalize them and engineer them, can be used for drug delivery as an application, in MRI, in the simplest as a pregnancy dipstick test, where you use gold nanoparticles for detection, in a glucose control unit, or in oil recovery for a host of applications. With that, I will take you to the tailoring that we do in our labs, meaning that I'm going to show you now how we do this and what do we gain out of these processes. So first and foremost, with the gold nanoparticles, and what we have done so far is that we synthesize these gold nanoparticles using a seeded growth technique, which means that we add some gold seeds, and then by controlling the reaction parameters, we change their size distribution, shape, morphology, and so on. It almost always starts with a mixture of two surfactants, which is CETA, which is a cationic surfactant, with a co-surfactant, which we vary from oleic acid DDAB, which is a double chain surfactant, so on and so forth. And then we add silver nitrate. So this process is called a silver assisted seeded growth because the silver ions help in controlling the dispersity of the particles and the growth rate. Then we add the gold precursor, so the solution becomes yellow. And then the moment we add ascorbic acid, it reduces the growth solution from Au3+ to Au+1. The solution becomes colorless. At this point, we add gold seeds, which are tiny 2 to 3 nanometer CTAP coated seeds. And then with time, the reaction progresses. Over 8 hours, we have our final particle with a shape and morphology that we want to have. Now, this method we have been working on for several years, and very recently we have seen that the effect of different surfactants or a binary surfactant. So in this slide, I'm going to quickly show you how by varying the ratio between a single chain surfactant such as CTAB with the double chain surfactant which is DDAB. The two surfactant structures can be seen on the top of the screen. We can vary the shapes from bipyramids to these tetrahexahedra to nanorods. Further, if we change the ascorbic acid and the pH, we are able to get H nanorods, dumbbell-shaped nanorods, and also if we use a completely different surfactant with an iodide group, we get longer tetrahexahedra and multifaceted structures. So this is just a teaser to show that by varying the ratio of the primary surfactant to a binary surfactant, we can tailor the different shapes of gold nanoparticles. Well, as you can see that there is a lot of parameters which can be changed. And this made us think for several years, how can we best depict these changes? And as my own background is from chemical engineering and with a specialization in colloids and polymer chemistry, we started to look if we can plot them or a ternary diagram. And many of you in the material science audience are very well accustomed to phase diagrams. So this is a typical diagram that we have now recently published for the first time in this literature, where we try to group the growth directing agents, the silver nitrates, the seed on one vertex, one side, the binary surfactant, which is also a reducing agent, and ascorbic acid, the main reducing agent, their ratio, and then the pH. Now, care should be taken here that the pH is a normalized pH, and therefore it can be plotted on a ternary diagram. What we have seen now is that if we draw these different tie lines, we are able to go from different shapes. So we are able to go from spheres to H nanorods to perfect nanorods. In another tie line, we see that there is no specific shape change, which is the nanomakura shape. A makura is a Japanese word for pillow. So these particles look like three-dimensional pillow. So along this, there is no change in the morphology. And along another line, we are able to see that there is changes in that from tetrahexahedra to more multifaceted structures. Now, what we, however, can't see on this phase diagram, if some of you are observing, is the point, the vertex around this pH, because there are several points clustered together. So we split them up, and then we see in pH, we remove the oleic acid. So this is for no oleic acid systems. And what we can see is that if we go in different directions of the pH, keeping the other factors constant, we can go from a very bad distribution of particles to nicer distribution. This means that
10 minutes left. 10 minutes left.
So the pH is a very important factor in this regard. So then further on, what I would show you is how these particles grow. And this is our presumption in the sense that there is first a reduction step. The hypothesis is that this is then transported to the seed surface. And on the seed, we have an autocatalytic reaction, which results in the formation of these different structures. And then we have a surface growth that results in these nice shapes. So there are two important steps that one should take into consideration: the surface growth and the reduction process, which are competing to form these different shapes. We move on into iron oxide nanoparticles. where I would show you two methods, as I said, co-precipitation, which is primarily you prepare a basic solution into which you drop a mixture of iron salts, which is Fe2 plus and Fe3 plus, and that results in the formation of magnetite nanoparticles. Another method that we very much use is the thermal decomposition or method. This is the first one where you use iron oleate. So you put them and then you inside a reactor with a reflux condenser and a finely controlled temperature. And depending upon what you use, whether you use oleic acid or whether you use sodium oleate, we get different shapes. So you can vary the shape from spheres to cubes, depending on oleic acid or sodium oleate, which are basically both passivating ligands as well as reducing agents. In another thermal decomposition, we widely use iron pentacarbonyl, which mostly gives us spheres, but here also we can vary the crystallinity of the iron nanoparticles, as I'll show you in the next slides. So this is a typical image of the magnetite. When you look at the cubes, they look like this, the iron oleate cubes, the iron oleate spheres, and the iron pentacarbonyl spheres. So these are all TEM images, and they show that if magnetite, you always get aggregated particles. If you don't use a stabilizer, that's the co-precipitation method. Whereas in thermal decomposition, you get very nice size distributions. The size distributions here vary between 10 nanometers to around 17 nanometers. So we cannot get big particles. If there is a requirement for bigger particles, these methods are not that good. On the other hand, if you look at the growth mechanism, as I said also with the iron oxide nanoparticles, this is a time-based TEM imaging done. Initially, you can see some needles, and then the first particles form with needles still there. And then if you look at these particles, there are lots of small particles and big particles. So they are polydispersed. Slowly and steadily with reaction time, they become more and more monodispersed. The final population that is around the size of 11 to 12 nanometer. So what I want you to show here is that the size of the particles slowly increase, whereas a polydispersity index gradually decreases. And this is an indication of the fact that there are secondary growth processes happening in which the small particles are most likely dissolving back into the solution and reprecipitating on the bigger particles, a phenomena which is called Ostwald ripening due to the solubility of the particles. With that, I would like you to take to functionalization, because all these particles are then made in an organic phase, meaning if you want to use them for biomedical applications, you need to transfer them into water phase. And that we do by using two kinds of processes. One is called TMH, which is a tetramethylammonium hydroxide, and TMAPS, which is this triammonium chloride, which helps in giving negative charge or positive charge, depending on the application where you want to go. So these are some data of the three particles that I showed you, the magnetite, the spherical nanoparticles, and the cubic nanoparticles. And as you see that the sizes are now 200, 400 nanometers, which means that we have aggregates of these particles stabilized by the tetramethyl TMH or TMAPS. And from the zeta potential, you can also get a very good understanding that the TMAPS coated particles are cationically charged, whereas the TMH are negatively charged. So with that, I would show you the final data regarding functionalization, where this is for the iron pentacarbonyl particles. And as you can see, that they are quite repeatable with a size range of 350 nanometers and good zeta potential. And also they are quite stable over several months. So this means that I have now given you a brief overview of how we tailor nanoparticles in order to control their shape, size, and morphology. If anybody in the audience is thinking that, okay, I showed you the nice cloth material, I showed you how to stitch them, now what is the application? Well, we have been working with a lot of these materials for over several years now in our group, but Corona times has actually shown us how and where we can use them. So I'll take you to the final part of my talk, where I'm going to introduce you very briefly to the current method that we developed, some of its key features, and what's the current status and where are we heading. So the coronavirus, I guess no one is unaware of it. So it is a highly contagious and a novel and dangerous virus. The reason it's novel and dangerous is because its genetic material is continuously evolving, and therefore we are getting newer and newer strains. What I want you to focus on this slide is the structure of a coronavirus, which has a lipid membrane, and then inside the lipid membrane, we have this RNA. So it's an RNA virus, so the RNA genome here. And what is very important to note is a spike protein, which is characteristic or called the S protein in the coronavirus, for which several antigen-based tests are being developed. So this test method, I will tell you very briefly why we went into this test method without going into the details of it. So there was 20th of March, Norway went into a corona lockdown on 12th of March. On the 20th of March, there was a request from the hospital, local hospital, for development of the NTNU for test kits. And between 20 and 22nd March, the other department at Clinical and Molecular Medicine, they developed certain methods without the magnetic beads. We came in on 24th of March when we were contacted. And within the first 3 days, we had some beads to test out. Between 27th and 29th March, this is a weekend, Sunday, when the tests were validated at the hospital. 1st April, we contacted the Norwegian health authorities. 3rd April, we filed 2 patents in 2 different countries for this method. And 17th of April, this was approved for use in Norway by the Norwegian health authority. So currently, all the diagnostic tests that happen in Norway are in the major hospitals are based on NTNU's test method. So this, as you see, is less than 1 month. We have been researching in this topic for over 10 years. And to get it from the lab to the hospitals took less than 1 month. And 17th of May, the Norwegian Health Authority signed an agreement with us for delivering 5.1 million test kits. So this was the end of March 2020 lab scale. As you can see, these are the beads we could produce in small vials. In mid of April 2020, we were a full team working in 2 production lines and a characterization unit and a quality control unit at the laboratory department. Over 30 people already involved and keeping separate production lines, so a small industry starting up within the university. How the test works, if you're wondering, this is a qPCR-based test kit whereby you take a nasal swab. The nasal swab is then put in a buffer solution, which then breaks open the virus. The genetic material is exposed, and at this point, our magnetic nanoparticles are put in. They bind to the genetic material. You use a magnet, separate it out. So now this is sticking to the magnet, the viral genetic material. You elute it in a solvent, and then you use qPCR to find out if this is corona or not. So our contribution to this method has been the development of the nanoparticles, and the most important thing, the scaling up, because it's not about testing few people, it's about testing the whole Norwegian population. So the basic principle is still the same as I mentioned before. I cannot give you more details about the exact process due to the confidentiality, but what we use is metal precursors and reducing agent. We synthesize these particles, the iron oxide nanoparticles, and then we coat them with a silica layer, forming these magnetic beads that are used for the corona diagnostic. And this is how the particles look like for those of you interested in microscopic images. So these are the beads that we're talking about, the magnetic beads. So why we are so important right now in this field of diagnostics is that we have a capacity to produce 1.5 million tests per week in the university labs. This capacity can be further scaled up. It's implemented in all major Norwegian hospitals for the COVID-19 diagnostics since early April. So we have a large validation data set. This is a high throughput system. So it works on different robotic platforms such as Kingfisher from Thermo Fisher, Tecan, Hamilton, Biomedical robots. And we can also use it for other kinds of pathogens. And as I said, this is patented. This is filed for patenting in 2 different countries. I'll show you a couple of slides on the data. So here you can see a comparison between a MagnaPure or a Roche sample test kit and our test kit. And you see that in all the cases, this was a 180 case setup. 175 out of 180 tests comply, which are better than the MagnaPure. If you have taken a bit of look Magna Pure uses 200 microliter patient sample. We use only 100 microliter patient sample. So there goes in how much input you put into the system. And the final slide that I can show you is the sensitivity of our batches. So as you would want these to be linear, we can detect up to 1 to 3 viral copies of RNA. And that's highly sensitive test in the market.
The
We have
time is
validated
over.
it.
The
Yeah,
time
I'm
is
on the
over.
last
Okay.
slide. Yes.
Okay.
1 to 3 copies of viral RNA, and this is quite reproducible. So where I will take you is that currently we are producing for Norway, and at the same time, we are also selling kits to Denmark and in India, and looking forward, and also in recently in Brazil. I'll take you to the final slide, which is the acknowledgement to all the people who have put in their hard work. As I said, it's a big team working on the Corona project, and we are also launching a new particle center. So some of you might be interested in following later on. And this is my group who has contributed to the presentation for today. The few of them who have been shown in this image, but for more information, you can visit the website and feel free to ask questions later on. Thank you.
Okay, thank you for Dr. Sulalit. There is very excellent and interesting topic that you have been presented. Because I understand you have the limit time. You just have time until 5 p.m. from Indonesian time. So there have a question from the chat box. So I will read. This is from Afrinda. How long the synthesis of AU and PS, and what the challenge during the synthesis of AU and PS? Thank you.
Yeah, so the process that we use here, it takes between 2 to 8 hours, depending on what shape and what size you want. So it's a very easy process in that sense. The only challenge that we have faced is that the purity of the chemicals. So the chemicals have to be pure. Otherwise, there are no big challenges for the synthesis process.
Okay, so we continue to the next question. This is from Dr. Engineering Bambang Ari. Could you comment on the health safety aspect of NT, which have been raised in the beginning of the discovery of the range of material around a couple of decades ago? Thank you.
Yes, that's a good question. I mean, the materials we are working with are biocompatible, and they are also cytotoxically, they are very low on the low side. But of course, they are nanomaterials. So if they are taken in, they are too small, some of the particles to go into the lungs or stay behind in the bodies. But the ones that once we functionalize them, as I showed you, they are, you can also call them half a micron than calling them 500 nanometers. So the materials we work with are, we work with those materials that we have tested also in vitro and in vivo and found out their cytotoxicity. There are a lot of other nanomaterials which can be health hazards. That's true.
Okay, thank you. But I have one question about your research that you are working on the nano gold for the medical application. So how you control the release ion of the gold in the human body? Because as we notice that human body contains a lot of solution. Can you explain
That's a very
about
good
this?
question. I didn't cover that in here. So what we generally do is that this gold would be enclosed in a polymer shell. So the reason we use gold is that we want to detect it using spectrophotometry. But in order to release the drug and to protect it from the body's immune system, we do a polymer coating, and most likely you have a PEG layer, which is polyethylene glycol, and that is used as a cloaking polymer. So it's very very much protected from the body's immune system.
Okay. Okay, I think that's all of the question from all of the participants. Thank you so much for Dr. Sulalit for the hot discussion and very excellent presentation. Now I will continue to the third keynote speaker. I would like to introduce the last keynote speaker in the second session. He is the Professor Shih Chen Shi, the Associate Professor Shih Chen Shi from Department of Mechanical Engineering at National Cheng Kung University. He has education background, PhD from Department of Material Science and Engineering, National Chiao Tung University, and he got the master from Department of Mechanical Engineering at National Cheng Kung University. He has also experience as associate professor in Department of Mechanical Engineering at National Cheng Kung University, assistant professor in Department of Mechanical Engineering, National Cheng Kung University, Metal Industry Research and Development Center, Neo Generation Biotechnology Corporation Ltd, Everlight Electronic Industry Corporation Ltd. And his expertise in metal process and microstructure analysis, micro or nano tripology, nanomaterial preparation, dispersion and application, and then photobiologic and photochemistry, LED design and application, particularly for optical simulation, stress and heat transfer analysis, cellulose material, particularly for biodegradable material, and the last is the composite material. He has received a lot of honors during his working. He also has a lot of patent from his research activity. He also gives a lot of contribution in publication. So for Professor Shi, I give the opportunities to you to share your presentation even in the last time. So please welcoming to Professor Shi.
Hello, can you hear me?
Yes, your voice
so
is very clear. Yes.
Share the, okay, this one. This one. So, yeah, is that okay?
Okay, yes.
Yeah,
yeah, it's clear.
Okay. Okay, good afternoon, Chair and all the audience. It's a great honor to speak here. I am Shi from National Cheng Kung University. Today, I want to share some information about the material called the cellulose. And the topic of this presentation is cellulose, interesting material. Okay. Okay, so this is the outline. First, we will start with the environmental crisis because we use a lot of plastic things and actually use this convenient material that will cause a lot of damage to our planet. And the second one, we want to find out some new material, one natural material, and that is really good from you can easily adapt from your surroundings like plants. And then the third part, we're trying to make it nano sized. So the nano sized material can have so great the properties. And then in this part, we also introduced the manufacturing process, how to extract the nanocellulose from the plants. And then we finalize with the 3 applications by using this kind of nanocellulose. Okay? Yes, this is what I say, because we use a lot of plastic, and actually the plastic is coming from the petroleum. So we have to dig so many holes in all over the planet and trying to have some gas or petroleum. And then sometimes we have to burn it, the gas, and you may cause the air pollution. And actually we know that maybe one day the petroleum will run out one day. And actually this kind of material, we have to extract it, and we have to modify it. So you cause a lot of air pollution, and it may be the reason for the climate change. And then the plastic is really convenient material. So we use it everywhere. And after use that, we just drop it. So, and where is the plastic? The plastic is just going to the river, and it can be eaten or it can be taken from the animals, especially for the wild animals. So plastic as a food, I think I think most of you may see this already in the meat land. Okay, so plastic as food, or plastic will be eaten by the small fish or small crab, and this plastic is our food. So we have to think about this. Is that the life that we need, that we want? Okay, actually before the COVID-19, this plastic is the severe damage to the wildlife. And you can see this as a terrible thing. The sea turtle just see the net, and this plastic just trap this turtle, yeah, like this. And actually the plastic bag just like very similar to the jellyfish. You know, the turtle just eat the jellyfish, so you cannot distinguish the jellyfish and the plastic bag in the sea. So we have to do something to trying to save them, because we can see the difference, but turtle does not. So is anything that we can do to trying to reduce the usage of the plastic material? Okay, after COVID-19, you know that there's one way to prevent the spreading of the COVID-19. And it has been successfully proved, especially in Taiwan, is that we use a lot of masks. But after use this mask, do you carefully wrap it or zip it and drop it to the trash can, or you just drop it? So you can see this the bandage of the mask just wrap the feet of the bird. And actually you can see a lot of plastic like mask, mask just floating around the sea. It's really terrible, especially for these wild animals. So we are thinking about, is there anything that we can try that can replace the plastic? So we try to find the resource just around us. Is that anything that can replace the plastic? Okay, maybe one thing, that is the cellulose. Actually, it's the cellulose is full in the plants. Okay, so you can see anywhere. And this is a paper from in 2016. It said, cellulose can get everywhere. And what is good in Taiwan? Actually, Taiwan is Taiwan is has a very good farmland like this. This is the eastern part of Taiwan called Taichung. You can see a lot of rice rod here, and actually this place is so beautiful. If you can just ride a bike just in the farm, it makes a lot of fun. But after we have this rice, how can we deal with the rice rod? It's only you can do the scarecrow only, or you can just burn it, but it may cause the air pollution. So maybe we can think about is that we can extract it from, we can have something from that rice rod. This is me, so I collect the rice rod in the farm and get back to the lab and trying to do something with this. Okay, so the cellulose, the lignocellulose material, it can compose with the lignin and hemicellulose and cellulose, and we are trying to adapt from cellulose from this plant. And this is the material is easily seen in the plants or rice rod or corn or even banana tree, any kind of plant, it has cellulose inside. So the point is that how can we do something to extract the cellulose from the plant? Of course you can't. And the size is really important of this cellulose material. If you use in the centimeter scale, it's like a wood, so you can use it as a building material, or you can want to nano size it to the very small size, and it shows like a sugar unit like this, or you can to combine the sugar unit together. It's just like a cellulose molecule like this. And this cellulose nanomaterial, it has a lot of unique property that can apply in so many applications. We will introduce later. Okay, the cellulose structure like this, and this is the sugar unit, and actually has so many intramolecular bonding and intermolecular bonding, hydrogen bonding, and this bonding will stronger the cellulose strong, and it can offer it can offer the very good property, especially for the mechanical property. And actually the cellulose looks like the 3D structure, so the strength and the hardness of this material is really good. Okay, and the third part, we're trying to make it in the nano material. So in this part, we'll introduce the manufacturing property. And actually, the first part of the nano-sized cellulose is the pulping. This process is really similar to the pulping process. So we use the alkali and process and the bleaching process that is similar to the pulping process. And first we have the rice straw, and then we use the alkali process. We use the NaOH solution to make it small, and then we use the bleaching process. However, in this process, normally we use the sodium hydrochloride, but this is not good for the environment. So we use in our lab, we use the photodynamic way to do the bleaching process. We use H2O2 solution in the UV environment. And actually, the process is really efficiently, with a high efficiency. We can reduce the bleaching time from 12 hours to 3 hours by using this photodynamic bleaching process. And the second part is the good things is that we don't need the sodium hydrochloride anymore because chloride is not good for the environment. Okay, so the first part of the process is the pulping process. And then the next part is to make the thing small, the cellulose small. And actually the nano-sized cellulose, it has two common style. One is the cellulose nanocrystal, cellulose nanocrystal. Sometimes we call it the CNC. And the second part is cellulose nanofiber. Normally we call it a CNF. Okay. After pulping material, it looks like this. At the pulping, yeah. And the slurry looks white because it just get through the bleaching process. Okay, if you want to get the CNCs, you have to break the amorphous region of the cellulose chain by immerse the material in the sulfuric acid. So this sulfuric acid will damage the amorphous region, and to break this CNC into very small aspect ratio. This kind of a CNC with the aspect ratio nearly 10. But if you just using this pulping material in the chemical and mechanical treatment and tempo oxidized treatment, this treatment only break the bonding between the cellulose chain. So you can have this kind of material with a higher aspect ratio, nearly 100. So like this, okay? So by using different process, you can have the different shape of the cellulose. This called the CNC, and this kind called the CNF. And actually, with a different aspect ratio, it has a different property, especially in the mechanical parts. Okay, this is the appearance of CNC and CNF. The CNC has an aspect ratio nearly 10. The CNF has an aspect ratio over 100. Yeah. Okay, so can we do something by using this nano size cellulose? The first thing, yeah, maybe we can try to use this material in this application, because you know the acrylic is widely used in the outdoor application like roll lamp. And actually, this is the LED roll lamp. You can see the LEDs over here, and this acrylic is serve as a lens, trying to modify the light pattern of the LEDs. And because of this, acrylic has a very good strength and transparency and the UV resistance, so it normally used in the outdoor application instead of PC. And also you can see the car lamp. The out shape of the car lamp is this material is normally applied by using the acrylic, or the sideboard is done by the acrylic. But the problem is that the acrylic is a brittleness, so easy to break when you ship it or you mount it, or even the bird just hit the sideboard, it may cause some damage. So we're trying to increase the brittleness of this acrylic. So the topic is, can we get some extra high toughness acrylic? Yep. First, so we just add the CNCs inside the acrylic. The first thing is that you have this kind of CNC immersed uniformly dispersion in the acrylic, that in the solution type, and then we're trying to solidify the acrylic. Then we can have this property. Okay, so the transparency is very important, because that is the unique property of acrylic. So you can see that with the small amount of CNC additive, the transparency is really high, nearly equal to the PNA, 92%. So the transparency is no problem. And how about the toughness? Okay, this is the original one. It has a strength at 5%, but after add some small amount of CNC additive, the strength can be extended to the 20%. So by adding this CNCs, we can successfully get the extremely high toughness acrylic. Okay, so if we want to apply this acrylic outdoor, but we need it's a toughness, so yeah, we solve this problem. So we get the very high toughness acrylic already. So the problem has been solved. Yes. Okay. How about the second application? This is the dental bath material. The acrylic is over here, and because this things will put into your mouth, so the biocompatibility is very important, and the strength of the acrylic is already good enough. However, the wear resistance should be improved, because your teeth, your food will have some damage on and wear on this acrylic. So we're trying to improve the wear resistance of this acrylic. So we just add the CNF inside the acrylic. We see that this is the pure acrylic, and this is the additive amount of CNF. You see, after adding just small amount of the CNF, you can successfully decrease the well volume by 66%. Okay, so the anti-well performance, the behavior has been increased by adding CNF. And how about the anti-well mechanism? Here we just show you the plot of well volume versus energy. The slope of this
10 minutes left.
Okay, the slope of this plot means it's relative to the coefficient of friction, but it also represents the well mechanism of this system. So you see that for the pure PNNA, the slope is like this. After adding some CNF inside, the slope has been decreased. So it means that there must something happen to reduce the coefficient of friction. By observing the well trap of the surface of the well tray, we can find that there's a S5 and 4. This is observed by the
We couldn't hear your voice. Professor Shi, we couldn't hear your voice.
Okay. This is the reason, this is the anti-well mechanism. So we have solved the problem of the easy wear of the dental base. Yeah. So by adding some CNF inside. So this problem has been solved. Okay, how about this? The application third. So this is a very new news that the East Japan Rail Company just branded antiviral coating material inside all the carriages because they think that this material can have the ability to kill the bacteria, and actually the CNF, the nano-cellulose can do the same thing. Okay, so we just doing these things. Okay, first I want to introduce a very good, nice food in Hualien. That's my hometown, the east part of Taiwan. So next time you visit Taiwan, you can try to find this. So we can call it. Sorry?
Oh, no, it's okay.
Okay, so this is called the bone scallion pancake. That is in Hualien, and that is not my point. My point is this pepper, and in our study we try to create some pepper called the green pepper because we're trying to strengthen the strength of this pepper and trying to increase the gas barrier of this pepper, and the most important part, we're trying to increase the antibacterial property of this bag because this bag is touching your food. So if this bag can have the ability of antibacterial, so it can protect you from the bacteria. Okay, so this is the point. This is the structure of the cellulose. It has so many bonding here. So if we can just modify, or we call it functionalize the surface of this bonding, it can bond with some photosensitizer at the light shine on, and this photosensitizer can convert the oxygen into ROS, reactive oxygen species, and this ROS can kill the bacteria. But the real thing is that we have to aldehyde the functionalization of this sugar unit, and actually to open this structure, and we can have the very active O here, and this O and OX is really active, and it can connect to the photosensitizer. Okay, this is the result for the bursting structure. Okay, compared to the craft paper or normally use the PE coated paper, and this is our coated paper. Yep, the bursting strength is a 22% increase by using this antibacterial coating. The strength can be increased. And how about the air permeability? Okay, only 2% of the crafted paper and only 10% of the PE coated paper. And how about the antibacterial coat, the behavior? Actually, after shining the green light, 60 minutes, you can see nothing, no bacterial can be found on the paper. So the antibacterial property is really good. Okay, so by using this CNC, modified or functionalized CNC, we can have this green pepper with a really high strength and low air permeability and with excellent antibacterial property. So the problem has been solved. Okay, thank you. Okay, here comes the conclusion. So because of the environment crisis, we're trying to find some material to replace plastic. Yeah, fortunately, we found some material called cellulose. It can be used to it has so many great properties that can be used to replace the plastic. So this material called cellulose, and we can easily extract from the rice rod. Actually, it can extract from any kind of plants, but the yield is the problem only. Okay, so cellulose can be applied to real world by its good additive property because its additive property is really good and high biocompatibility. You can use it in your mouth, in your body, even in your blood, because the cellulose have a really good biocompatibility and high surface area to volume ratio. So you can modify the surface, you can functionalize the surface, and this nano material can combine with even like a drug or something that can photosensitizer. You can do a lot of things by using this high surface volume material, small material. Yeah, this is my kit. This is the real very good transparent PMMA with CNC inside. Okay, thanks for your listening. And I'm seeking for the operation. If you are interested in the biomaterial, photodynamic inactivation, or tribology, or bioimage, yeah, we can talk. Yeah, thank you. Thank you for your time.
Okay, thank you so much for the Professor C. That is very interesting and excellent presentation. Right now, I would like to open the discussion. I want to make an announcement that really sorry that Dr. Sulalit have been late at 5 p.m. because he has another appointment. So the discussion will be involve Professor C and Professor Erkan. First of all, for Professor Shi, this has been entrance to question. Dear Professor Shih Chen Shi, would you like to comment the stability mechanism of acrylic emulsion prepared using nanocellulose? From the chat box. There are two
book, yes.
Chat box, yes. Would you like to comment the stability mechanism of acrylic?
Stability mechanism?
Yes.
Ooh, I don't see it in the chat. Sorry. Stability of the. Sorry. Stability of.
Stability of acrylic emulsion.
Emulsion?
From Muhammad Farid. Yes, from Muhammad Farid in the chat book. From Muhammad Farid at 5:02 p.m.
Okay, let me check. Come out the stability mechanism of
Yes.
accurate
Yeah.
emulsion prepare using nano.
Right.
Okay, okay, I got it. Okay, you know, there's so many process, accurate formation process, but in our lab, we just trying to emulse the nano. Yeah, okay, I got it. So we have to modify the surface of the cellulose first, and it can, because the cellulose is hydrophilic and the agar is hydrophobic, so we have add some surfactant to, like the hydrophilic substance can evolve into the hydrophobic material, the solution. That we have to do this first, by checking the uniformity stability of the nanocellulose inside the aqueous solution, precursor solution, and then we just do the next step, try to solidify the aqueous. Yeah. So after the answer is that we have add some surfactant to try to bind this cellulose and MMA precursor. Yeah.
All right, so now we move to the next question is from the Dr. Engineering Bambang Ari. Could you comment on the binding ability of the nano-derived cellulose, such as what we can have from CMC cellulose? Thanks.
Okay, I think CMC is one derivative material from the cellulose. And actually, I use HPNC a lot before this cellulose. So I think this kind of material should be the hydrophilic, so they can bind easily. If or we can have some functionalized to the cellulose, and it is easily achieved by using maybe tempo solution, and you can open the sugar unit and become a aldehyde function group, and then this kind of surface easily to combine with the other material. Yeah, so it's no problem with that.
Okay, so now the third one question. Can we synthesize the cellulose or maybe an artificial wood in lab rather than by cutting down trees to obtain the lignin or cellulose? Thank you. The last.
An artificial wood.
Yeah.
Sorry, artificial wood means well, actually you don't need to cut the woods first, because that's what I say, that the cellulose can be found in all kinds of plants, bamboo, rice, banana tree, corn. So you can find it everywhere. So the point that I'm trying to emphasize the importance of this material is that you can get it everywhere, just like your flower, just like your whatever grass. So is that okay? So you can have this kind of cellulose everywhere. So no need to cut the plants. That's not my point. I want to save the forest, so don't cut the trees. Yeah.
Yes, or maybe we can produce the cellulose is from the waste, like a pepper plants or some things that has been not used during the production. I think that's will be potentially for the raw material of cellulose. The waste from the paper industry.
Yeah, sorry, pardon?
Or maybe we can make it the cellulose is from the waste, like for example, from the waste of paper industry. So there is a lot of paper waste. Probably
No,
we
actually
can.
not.
No? Oh, okay. Because I read some.
Because the waste of the popping is normally the lignin. Lignin is not can be. Yeah, this lignin is you know, it has some flavor and it's dark, and actually it's not the cellulose inside. So the waste of the popping is not the cellulose, it's lignin. That's it. It's really waste.
Oh, okay. Thank you. So I think that's all of the question for Professor C. And then I would like have question to Professor Erkan. So Professor Erkan, I'm working on the EBM manufacturing, particularly for the hypothesis joint using the cobalt chromolybdenum alloy. So during the EBM manufacturings, we using parameter, and then we produce a transformation and evolution of the microstructure from the along of the rod from the top and the bottom. But as we noticed that during the EBM production, we using the preheating is surrounding 700 degrees Celsius. So the purpose in here is try to avoid the huge difference of temperature from the source of electron beam and to the solidification rate. So basically from your experiment from the peridynamics, it is possible to investigate the cracking during the transformation of the material, because I have been studying for the deformation, particularly for the cobalt chromolybdenum. So what do you think that we have to start it, which part that will be influenced for the prediction of the preheating? Just try to avoid of the cracking during the solidification from the EBM manufacturing. Thank you.
Thank you very much for the question. So basically, this is, in terms of modeling, this is a little bit kind of a complex situation, because as you see, there is kind of an interaction of multiple fields included in this particular process. It's not just the mechanical deformation that you see. So, as part of the process, based on what you described, we have temperature change, or the effect of temperature that we need to take into account. But that's something that we can do as part of the process. And then, in addition to this, what I see from what you just described, there is a phase change and a solidification process. So we also need to actually model that particular situation as well. And as part of this, also we need to look at the mechanical field to find the cracking. So this is something basically that we can do by using peridynamics and try to then find out basically why these cracks are occurring as part of this process. And then basically this is kind of the idea of also using computation modeling so that we can actually do some type of parameterization study, in a sense that by changing different basic parameters, then we can achieve a condition that basically we don't have those cracks there. So this is doable, as I said, but this is kind of a complex problem. But by using peridynamics, we can do it.
Oh, okay, thank you. Because we have been trying with several instruments of the additive manufacturing. So our labs, when I was a PhD in Japan at EMR, Tohoku University, we have been trying using the LSM, using the laser additive manufacturing from the USA products. But we found it a lot of from the laser has been produced of crack during the solidification in additive manufacturing. However, when we using the EBM from the Arkham and we make the preheating from 700, so it's mean we reduce the solidification time. So that's why we produce much better. However, during the evolution, we recognize that the evolution is still occur along the route when we have been produced for more than 10 centimeter. If less than 10 centimeter, we still have a one phase homogeneous. However, when we produce longer than 10 centimeter, we have some evolution of the phase. So it look like gamma to the epsilon if in cobalt chromolybdenum. So that's why if we want to make the efficiency of manufacturing process, which part of the heating that we have to choose, because the higher of the heating, that means we produce a lot of cost of the production. So that's why probably for the next, really interesting to using the peridynamic for the investigation cracking during the solidification of EBM, particularly in cobalt chromolybdenum. Thank you so much.
Sure.
That's my question. Is there any question for the other audience? Because I believe
Yes, Dr. Yuli.
Okay, thank you. We have another question.
Yes.
Welcome.
Yes, I have question for Prof. Erkan. Prof. Erkan, nice to meet you again.
Nice to meet you, Prof. Irfan.
Okay. As we know, most interesting technology development in material science is nanotechnology. My question is, how is the applicability of peridynamics in solving multi-scale problems? Does the peridynamics anticipate problem related to failure at nanoscales? Some example could be some example given as well. Thank you very much, Prof. Erkan.
Thank you much, Professor Irfan, for the very nice question. So I think this is one of the advantages of peridynamics that I didn't really have time to talk about. So, you know, when I was describing peridynamics, we have this parameter that we call horizon. So horizon is basically the influence domain range, which describes basically the domain which limits the interaction between material points. So we call also this is some type of length scale parameter. And length scale parameter normally doesn't exist in classical quantum mechanics. That means that if you analyze a structure at kind of a large scale, and if you try to use the same model at nanoscale, you will realize that you will get exactly the same result, because there is no influence of the length scale in the formulation. But in peridynamics, the story is different. So because of this length scale parameter within the formulation, now actually we can choose a particle horizon size to describe the physics of the problem at the nanoscale. And basically, we can also see this based on the wave dispersion curves. So, you know, all materials actually has wave dispersion curves. And these wave dispersion curves, if you look at, for example, metals and so on, you see that they are nonlinear. But if you look at what finite element or classical quantum mechanics is providing us, is just a linear relationship for the wave dispersion curve. It's kind of basically telling us that classical quantum mechanics or finite element analysis is just limited for the situation that we can only use long range, actually wave situation. So we cannot actually capture what's happening. The things are happening at a small scale. So basically, I just want to keep it short in a way that I use the horizon by assigning the horizon size properly. Actually, we can capture non-local effects, which normally occurs at nanoscale.
Yes. Okay, thank you, Prof. Erkan. Maybe last question. What about a relationship between peridynamics and massless methods like smoothed particle hydrodynamics? Is there any relationship between the two methods?
Well, that's also another nice question. So, as I was trying to explain, basically, you know, peridynamics is a continuum mechanics formulation. So it is not actually a numerical technique by itself. So, and as I was also talking about, actually the basics of quantum mechanics was established 200 years ago. But after that establishment, basically, there are many different now quantum mechanics formulations available for different types of problems. But when we normally talk about quantum mechanics, people normally refer to the Cauchy's formulation. But as I said, there are many other formations which are currently available, and peridynamics is one of them. But as I was also trying to explain, the way that we describe equation of motion, it is in integral form, which doesn't contain derivatives. So that's why I would like to use peridynamics for cracking problems, because there are discontinuities in such problems. So now if you go back to the original equation, which is this integral equation, unfortunately, we cannot solve that equation by using analytical means. So because of that reason, we, like what we do in finite element methodology and many other techniques, we use numerical approaches. And meshes approach is one of those approaches that we can use, and actually it's the standard approach that we use to solve our integral equation. So as I said, meshes approach and peridynamics, actually they are kind of different things. So we are using meshes approach to solve our equation of motion. But once we basically discretize our system based on meshless methodology, then the equations that we obtain, it looks very similar to smoothed particle hydrodynamics or molecular dynamics and so on. So once we discretize our system, but the foundations of these methodologies, they are totally different from each other, although their equations, they look similar to each other, okay? So peridynamics, although I was trying to explain how we derive the equation of motion, actually coming from the really fundamentals of quantum mechanics. But if you look at these other numerical techniques, they are mainly actually numerical. Okay, so if you think about smoothed particle hydrodynamics, so smoothed particle hydrodynamics is actually depending on a mathematical trick. So, and it is based on, actually, it's coming from the concept of delta function. So if you think about a delta function, actually you can use delta function to express a kind of function at a particular point. So, but the delta function is a very, irregular function in a sense that it is very, it increases rapidly, it goes to infinity and so on. It's not an easy function to deal with. So because of that reason, what people did is they smoothed the delta function in a way that now they also describe some type of horizon. And then from that horizon, they said that, okay, to calculate a function at a particular point, actually, we can calculate it based on the other other points inside the horizon. So it does some type of basic interpolation. So as you see, smoothed particle hydrodynamics is kind of a numerical concept rather than actually kind of a fundamental quantum mechanics concept. So that is basically the main difference in between.
Okay. Your explanation is very clear. It's very interesting. Thank you very much, Prof. Erkan. Hope we can extend or develop further collaboration between universities.
I have so too.
Thank you very much. Thank you,
Thank you,
Dr. Yuli.
Okay, now the last question is for Professor Shi from the chat box. Is that possible to extract the cellulose without any acid or alkaline solvent? Probably the purpose is for green technology methods. I'm sorry, we couldn't hear your voice. It's still on the mute.
This one. Yeah, is that okay?
Okay.
Yeah, sure. You can get the cellulose without the acid or alkaline, but normally you should apply so strong the mechanical force like a grinding or the water jet, just collect the cellulose in together. So by this strong mechanical force, you can open the wrap or the bonding of the plants, and then you can get the cellulose, but only the cellulose nanofiber that you can get, because you cannot using the mechanical force to break the amorphous region of the sugar unit. So the only thing that you can get is CNF by applying strong mechanical force, but you can get the CNC without using the acid or alkaline. But the point is that if you're using the strong mechanical force, you will consume a lot of energy. So that's not an efficient way to get the cellulose by this method. So that's not recommended to use this kind of approach. Okay. Yep. Sorry, I can't hear you.
I'm sorry, how about if another opportunity like we using the microwave assisted, because as we noticed that microwave assisted now is attract interest people for organic synthesis. So what do you think? Is this possible or not? We can be synthesize the cellulose by using the microwave assisted.
Sorry, microwave.
Assisted.
Microwave.
Yes, for irradiation. Is possible or not to make the changes function group of cellulose?
But normally it will cause the you know the cellulose just like a pepper. So you give me so higher the energy you will burn. So I don't think, but maybe in the low energy like atmospheric plasma, maybe you can do that. I have no idea with that, but if the plasma has too high the energy, the cellulose will burn just like a pepper burn. We can smell the flavor that just like the pepper. You burn the pepper. So yeah, but for the traditional plasma treatment, I don't think that is a good way to get the cellulose from the plants. Yeah.
Okay, so until right now, the method is still using the chemical.
Yeah, because it's much more efficient way.
More efficient.
But yeah, but we in our lab we're trying to make everything green, so we are trying to use a lot of way to get the cellulose. Yeah, I think that's that's the you know the ongoing project. We're trying to make it all the process green. Yeah.
How about the enzymatic methods degradation for the cellulose synthesis?
Yeah,
It's possible.
Yes. Sure. Someone get the cellulose from the bacteria. So they use the way of an enzymatic way.
Regarding from the point of view, the effectiveness from the cost production, which are the more effective using the chemical method or enzymatic?
Enzymatic, sure, of course, chemical.
Enzymatic.
No,
it is chemical. Chemical, okay,
yeah,
because
of course.
for enzymatic, I believe it's difficult to control.
The strength of the chemical is that you can make it mass production, right? You can make it a big tank.
Yeah.
You just put everything inside and try to roll it, hit it, and can have a lot of yield. Yeah, I think that's the benefit of the chemical. But yeah, we're still working on that in a green way. So just wait.
Okay, thank you so much, Professor Shi and Professor Erkan, for the hot discussion today. And thank you for all of the audience for attending this conference overall. So I will be written to the presenter because the session in the second presentation has been done. So thank you so much for all of your supporting. Thank you so much from the committee of ICOMMET 2020.
Dr.
Okay.
Yuli.
Thank you, Oterkus.
Thank you very much.
Yeah.
Okay, thank you.
Dr. Yuli.
Yes.
Okay. We are ready for closing ceremony, but I hope all keynote speaker can still stay for the photo session.
Oh, okay.
Yeah, okay.
So I can smile now?
Yes.
1, 2, 3.
Please.
Yeah, okay, done. Thank you very much.
Thank you so much.
Yeah, coming back to
audience and keynote speaker.
We would like to say thank you very much to all the speakers for the very comprehensive and fruitful discussions. Excellencies, after all the sessions we had today in our conference, we feel like we should do something memorable for each of you. So by this, we will end the day by announcing the best papers.
So now, we will begin the awarding ceremony for the best paper of ICOMMET 2020. Through deliberations, the winners of the best paper go to
Ms. Tita Octavia Cahya Rahayu and team with the title Modification of Gold Substrate with Magnetite and Graphene Composite as a Surface Plasmon Resonance Biosensor-Based Material.
Bambang Iskandriawan and team with the title Structure and Material Analysis in the Inserted Stature Chamber to Prevent Transmission of COVID-19 with Numerical Simulation Method.
The next is Atria Pradityana and team with the title Effect of TIN Coating to Corrosion Rate in the Simulated Body Fluid Solution.
Hafid Suharyadi and Toga Sugeng Subiarto with title Enhanced Corrosion Resistance of Carbon Steels by Graphene Epoxy Coatings.
The next one is Destri Mulyastri and team with the title Percentage Reduction Analysis of Flow Stress of Steel IC 1006 by Finite Element Method.
Andromeda Dwi Laksono with the title Comparison Study of Mechanical Properties of Wood with the Composite Polyester Wood Powder.
The next one is Natalino Fonseca with the title The Effect of Chill Thickness to Microstructure and Surface Hardness Layer on Specimen Ductile Cast Iron. Once again, congratulations to all the winners. Now, we would like to welcome Dr. Mas Irfan Purbawanto Hidayat as the chairman of this conference to give the closing statement.
Yeah. You have presented your research works enthusiastically and gathering together for prospective networking and collaboration. Eventually, this event has come to an end. I wish all of you enjoy this fascinating event and coming back with new ideas and wonderful experience. Once again, thank you very much for all our keynote speakers. Baik saya yang alhamdulillah and thank you. I am officially close this virtual event ICOMMET 2020. See you again at the 5th ICOMMET 2021. Thank you very much. Very good afternoon. Wassalamualaikum warahmatullahi wabarakatuh.
Like all of the meetings, it finally came to an end. But let us thank the committee and the audience entirely. May what we have conducted will be useful for us. Thank you for your participation in the 4th International Conference on Materials and Metallurgical Engineering and Technology 2020. I'm Salsa.
And I am Rafi.
See you on the next year ICOMMET. Have a great day. And finally, wassalamualaikum warahmatullahi wabarakatuh.
Thank you. Bye-bye.
Thank you, everyone.